Good day, everyone. My name is Sedi, and this is the discussion for the Module 4 of Basic Calculus Inserts DMAT. So we will discuss here the derivatives of the other transcendental functions that we haven't discussed in Module 3. We already discussed the algebraic derivatives, and we already discussed the first transcendental function, which is the exponential function derivatives. We will take a look at the other 4 transcendental functions and their derivatives for this lesson. Without further ado, let us begin. Transcendental functions are functions which cannot be explicitly defined using purely algebraic terms. This means that you need to insert something like a function which denotes this type of function, or something that you need to involve algebraic terms in exponents. Some of these functions are the exponential functions, which we already discussed in Module 3. Then trigonometric and inverse trigonometric function. And lastly, logarithmic functions, which is basically the inverse of exponential functions. The first set of derivatives that we will discuss are the derivatives of trigonometric functions. The derivative of sine u with respect to x is cosine u du. The derivative of cosine u with respect to x is equal to negative sine u du. Then the derivative of tangent with respect to x is equal to secant squared u du. Then the derivative of cotangent u is equal to negative cosecant squared u du. Meanwhile, for secant and cosecant respectively, we have secant u tan u du and negative cosecant u cotangent u du, respectively. We need to note that this du represents the function u in terms of x, which means that in trigonometric functions, we always utilize the chain rule. And one example of this is this problem. Evaluate the derivative of sine 3x. As we can see, unlike the one that is given there, we need to utilize the chain rule for 3x, since the derivative of sine x alone is cosine x. However, with other functions and other variables inside the trigonometric function, the derivative changes. So first, we consider the sine and 3x as two different functions. So by the chain rule, we first get the derivative of the outside, which is d dx of quantity sine 3x is equal to cosine 3x. The derivative of sine is cosine, and we will leave a d dx 3x since we need to use the chain rule so that we can differentiate 3x. Then we get cosine 3x multiplied by quantity d dx of quantity 3x. This gives us 3, and multiplying it to cosine 3x gives us the final answer, which is 3 cosine 3x. Next example. Evaluate the derivative of tan x raised to the 4th power. So as we can see, this exponent here on tan implies that we need to use chain rule, but instead of the earlier problem in which the algebraic function is the one inside the chain or the other function, the one that is inside this time is a trigonometric function, which is why it is a separate example. So we have the first derivative with respect to x of quantity tangent x raised to the fourth power. So we do normal algebraic differentiation to this one. So the 4 will be multiplied and the exponent of tangent x will be subtracted by 1. So we get 4 multiplied by tangent x cubed. Then the function tan x, which is the inside function, will be differentiated. So we leave a ddx of quantity tangent x. And the derivative of tangent x is secant squared x. So when we multiply that to the first part of the derivative, which is 4 tan x cubed, we get 4 tan x cubed secant x squared as our final answer. For the third problem, we have this one problem. So as we can see, it is a combination of the trigonometric function being inside and another algebraic function inside the trigonometric function. So we will utilize chain rule again. So we have the first derivative of quantity sine quantity 5x plus 1 cubed is equal to 3 sine squared quantity 5x plus 1. So we subtracted 1. This is a typographical error. It should be 3. Then we differentiate quantity sine 5x as quantity sine 5x plus 1. So we use chain rule again on this second function that we obtained, which is sine quantity 5x plus 1, to get 3 sine squared quantity 5x plus 1 cosine 5 quantity 5x plus 1, and the derivative of the final function inside, which is quantity 5x plus 1. If we differentiated 5x plus 1, we get 5 using normal differentiation rules. So we multiply all the derivatives that we obtained using the chain rule. So we get 3 multiplied by sine 5 quantity 5x plus 1 squared multiplied by cosine quantity 5x plus 1 multiplied by 5. We can only multiply the constants. So we get 15 sine quantity 5x plus 1 squared cosine quantity 5x plus 1 as the answer. So for the exercises of this portion of the lesson, we have 4 items. I will try to do number 4, which is a type of problem that I haven't discussed. So we have cosine of cosine 2x. So we have this given. So we differentiate this one first. The derivative of cosine is sine, negative sine rather, and we keep the inside term inside that derivative. Then we note that we still need to differentiate the term inside, which is quantity cosine 2x. This is equivalent to negative sine cos 2x, then the derivative of cosine is negative sine, right? Negative sine 2x. But still, we need to note that we still need to differentiate the term inside the cosine, which is 2x. So we place the derivative of 2x. Now, finally, we have negative times negative is positive. So these two will become positive. And we have sine multiply cosine 2x sine 2x. Then finally, the derivative of this one is 2. So we have times 2. So the final answer for this problem is 2 sine of quantity cosine 2x multiplied by sine 2x. So this is our final answer for this problem. You can try 1 to 3 alone since I already discussed it. But for this problem, here is the final answer. Now we proceed with the second function, which is the logarithmic function. So we only have two things to memorize here. The first one is the case where the given logarithm is the natural logarithm, which symbol is ln. The first derivative of ln u with respect to x is equal to 1 over u multiplied by du, which is the derivative of the function u with respect to x. Then the derivative of logarithm of u base a is equal to 1 over quantity u ln of a, where a is the base of the logarithm, du. As we can see, we have the a. If we replace it with e, or the Euler's constant, it will become the derivative for ln a. And ln of e is equal to 1, which is why the ln a is removed on the first derivative. Now for the examples. First example, find the derivative of the natural logarithm of quantity 3x squared plus 7x. By utilizing the chain rule, we get the derivative of the outside function, which is 1 over quantity 3x squared plus 7x. Then the term inside, which is quantity 3x squared plus 7x, should be differentiated next. So the derivative of that function is 6x plus 7. And we multiply it on the first result earlier to give us the final answer, which is a rational function, quantity 6x plus 7 all over quantity 3x squared plus 7x. Another example. Find the derivative of logarithm of quantity 1 minus 5x base 4. So we will utilize the second form of the logarithmic function derivative. By using chain rule again, we easily get first derivative of the given function is equal to 1 over quantity 1 minus 5x ln 4. Since we need to differentiate the term inside the function, which is 1 minus 5x, we get another factor, which is negative 5, right? So we multiply these two and get this final derivative, which is negative 5 all over quantity 1 minus 5x multiplied by ln 4. Now, here are some exercises. You can do 1 and 2 for yourselves, but I will try to answer number 3. So we try number 3, which is the natural logarithm of cosine 2x. So first, we get the derivative of the outside function, which is the natural logarithm. So we get 1 over cosine 2x multiplied by the derivative of the inside function, which is cosine 2x. Then we will use the derivative of trigonometric function to get 1 minus cosine 2x. So when we differentiate this one, we get negative sine 2x. Then the derivative of the inside function of cosine 2x, which is 2x. The derivative of this one is simply 2. So we have the final function 1 over quantity cosine 2x multiplied by negative sine 2x multiplied by 2, which is equal to negative sine 2x over cosine 2x times 2. Using trigonometric identities, we can further simplify this one into negative 2. We know that sine over cosine in our junior high school trigonometry or pre-calculus trigonometry, sine over cosine is tangent. So 2 negative 2 multiplied by tangent 2x is our final answer. So it is important, by the way, for you to have a background knowledge of some of the trigonometric identities, which are discussed already in the pre-calculus that you took or that you have encountered. Now, we will move on to the second last differentiation group, which is the inverse trigonometric functions. Now, for our third function, we have the derivatives of inverse trigonometric functions, which is sine negative 1 u. This is called as arc sine or inverse sine, but I would call them arc. So we have arc sine, arc cosine, arc tangent, arc cotangent, arc secant, and arc cosecant. So for arc sine u, the derivative is 1 over quantity square root of quantity 1 minus u squared du. For arc cosine, we have its negative counterpart. Negative 1 over square root of quantity 1 minus u squared du. For arc tangent, we have 1 over quantity 1 plus u squared. For cotangent, we have its negative counterpart, which is negative 1 over quantity 1 plus u squared. For secant and cosecant, we still have the positive and negative of 1 over absolute value of u multiplied by quantity squared of quantity u squared minus 1 du. And it's negative respectively. So let's have some examples. First, find the derivative of arc sine 4x. Using chain rule, we get the derivative of arc sine 4x with respect to x is equal to 1 over square root of quantity 1 minus quantity 4x squared multiplied by the first derivative of 4x. Since we utilize chain rule, we will differentiate the term inside the given function, which is arcsine. Simplifying, we obtain 1 over square root of quantity 1 minus quantity 4x squared times 4, since the first derivative of 4x is 4. Multiplying these two and simplifying the term inside the square root, we get 4 over square root of quantity 1 minus 16x squared. Another example, this time we will use arctan. Find the derivative of arctan quantity 8x plus 1. So the derivative of arctan is 1 over quantity 1 plus u squared du. So we will use chain rule to get 1 over quantity 1 plus quantity 8x plus 1 squared multiplied by the derivative of the term that is inside, which is quantity 8x plus 1. The derivative of this is 8. So we have 1 over quantity 1 plus 64x squared plus 16x plus 1, which is 8 over quantity 64x squared plus 16x plus 2. However, we can get this one into lowest terms as we have a common factor, which is 2. So we have 4 over 32x squared plus 8x plus 1. So this is our final answer. Now we will discuss the final differentiation rules, which is hyperbolic functions. So this might sound unfamiliar to you, so I will reintroduce them in case if you're not familiar with this. Hyperbolic functions are exponential functions in terms of the exponent e. So we have hyperbolic sine, which symbol is sine with an h at the end. Hyperbolic cosine, which symbol is cosine with an h on the end. And define all the other hyperbolic functions similarly as trigonometric functions with just the h at the end of their symbols. So from tan, we have hyperbolic tangent. Cotangent, we have hyperbolic cotangent. Second, we have hyperbolic secant. And lastly, cosecant, we have hyperbolic cosecant. So the hyperbolic sign is defined as e raised to the x power minus e raised to quantity negative x power all over 2. Then the hyperbolic cosine is opposite in terms of the sign between the positive exponent x and negative exponent x. If hyperbolic sign has a negative sign in between, hyperbolic cosine has positive. Then we apply the same trigonometric identity to get tangent, the hyperbolic tangent. We divide the hyperbolic sine by the hyperbolic cosine to get this term. Meanwhile, cotangent, same as the normal cotangent, the hyperbolic cotangent is also obtained in such a way. The same goes for hyperbolic secant and hyperbolic cosecant, in which you need to take the reciprocal of cosine and sine respectively. So the derivatives of each of the hyperbolic functions are as follows. The derivative of hyperbolic sine u with respect to x is hyperbolic cosine of u du. the derivative of hyperbolic cosine u with respect to x is hyperbolic sine u du. As you can see, this is different from the trigonometric one. The trigonometric cosine, when differentiated, gives us negative sign. But here, the derivative of hyperbolic cosine has the same sign as the one differentiated. So, positive, positive. Hyperbolic tangent's derivative is the square of hyperbolic secant, which is pretty much like the derivative of trigonometric tangent. The same goes for that hyperbolic cotangent. It is identical to the derivative of normal cotangent, which is hyperbolic cosecant squared but negative. However, the difference here is the hyperbolic secant, whose derivative, instead of positive secant tangent, which is the one in trigonometric secant, we have negative hyperbolic secant multiplied by hyperbolic tangent. Then the du for the chain rule. Then the hyperbolic cosecant is pretty much the same as the normal cosecant earlier, which is negative hyperbolic cosecant u, hyperbolic cotangent u du. And now that we're at it, let's try some example problems. Find the derivative of hyperbolic sine 4x. Then, using chain rule, we get the first derivative of hyperbolic sine 4x is equal to hyperbolic cosine 4x multiplied by the derivative of the term inside the hyperbolic sign, which is 4x. The derivative of 4x is 4, so we just multiply it to the hyperbolic cosine of quantity 4x to get 4 hyperbolic cosine quantity 4x as the final answer. Lastly, we have this problem. Find the derivative of hyperbolic tangent of quantity x squared plus x. So we utilize the chain rule again to get the first derivative of hyperbolic tangent quantity x squared plus x is equal to hyperbolic secant quantity x squared plus x squared multiplied by the first derivative of the term inside the hyperbolic tan. The derivative that we need is 2x plus 1. When we differentiate x squared plus x, we obtain 2x plus 1. Multiplying it to the hyperbolic secant x squared plus x squared, we obtain the final answer of quantity 2x plus 1, second hyperbolic secant of x squared plus x squared. As we can see, differentiating transcendental functions often require the usage of chain rule and, of course, the other fundamental differentiation processes. Deriving each rule will be a bit hard, so it is better if you will memorize each of the rules. There are 6 for trigonometric, inverse trigonometric, and hyperbolic, and 2 for logarithmic. So all in all, there are 20, but even so, hyperbolic and trigonometric are pretty much the same except for cosine and secant derivatives. So that is it for module 4. I hope you learned something from this video and good luck on your quizzes. Thank you.